Good morning, everyone. We're going to pick back up here in chapter 4 today. So we're coming back to precipitation reactions. I was rushing through a demonstration at the end. I'm going to come back to that demonstration a little bit later in the class. But let's start here with this chart here. This is our solubility guidelines. This is how we can predict the water solubility and then ionization trends of ionic compounds. So this chart here, this is for ionic compounds, so metal, non-metal. And what we're looking at is, again, as a review, that our soluble compounds that contain nitrate, acetate, chloride, bromide, iodide, and sulfate, these ions here, when paired up with metal cations, are going to form soluble compounds. So you take a metal, mix them with those ions, you get a water-soluble compound that completely ionizes. And so all water-soluble ionic compounds completely ionize in water, but there are some exceptions. So if you took like silver chloride, it turns out to be insoluble in water. So KCl in water dissociates into K plus ions and chloride ions. Each individual ion at the atomic level has its own little water sphere separated from all the other ions. So you have a plus ion, a minus ion, and a bunch of those floating around solution. You don't have K plus and Cl minus stuck together anymore. So they separate into water when it dissolves. So the dissociation process, the way these compounds that do dissolve in water do so is by each ion surrounding by water. So imagine you have a solid, a piece of water, an ion falls off the metal, dissolves by water. That's the solution process. That's a fun wake-up song, I think. So then mercury 1 is that weird ion where the Hg2 2+ is what we call the mercury 1 ion. So this ion here is a little bit weird in that you have two mercury atoms bonded together with a net charge of 2+. It's kind of like O2, 2-. So it's kind of like a molecular ion, but of metals. So it's two metals bonded together with an overall charge. But then there's also Hg2+, and that's not one of the exceptions. So Hg2+, the ordinary mercury 2 cation, which is a common cation of mercury, is not one of the exceptions. So it's just a weird thing where Hg2I2 would be insoluble in water, wouldn't ionize, but HgI2 would be soluble. So a solution of mercury 2 iodide in water would be mercury 2+, an iodide ion, whereas the Hg2I2 would just be a solid at the bottom of the test tube, would not be ionized. And so then we have some compounds that are generally on the insoluble side when compounds contain those ions. So those are sulfide and hydroxide. And interestingly, if you look at the solubility guidelines, the exceptions for the top and the bottom of the chart are the same as each other. And then the middle ions, their solubility trends are the same as each other. If you look at this rule here, that all common ICs, all ionic compounds that contain ammonium or alkali cations, that's our first group, lithium to cesium, any compound containing those cations is going to be water soluble. So you know that those compounds with carbonate and sulfate carbonate and phosphate, that those have to be water soluble. So the exceptions for carbonate and phosphate would at least have to include ammonium, the alkali cations, and it turns out to be only those ions for those two. And then sulfide and hydroxide pick up the ions of also calcium, strontium, and barium. So we're adding these to the list. But you get this chart for exams. You don't have to memorize the chart. You just have to be able to use it and interpret. The top half are generally soluble compounds, the bottom half generally insoluble compounds, and then the bottom half, the exceptions are soluble. On the top half, the exceptions are insoluble. So you just have to keep the difference between insoluble versus soluble ions and the general compounds that are so according to the chart. And so this is the kind of page we're leaving off in our notes from. Let me also note that if you grab the notes from last time, I did make a change and I re-uploaded with the exact same file name, and I put a little note in our lecture file. It's like slides 11 to 15 are going to contain just a different example that'll match up with the demo that we're going to do with that. So if you wanted to grab at some point or just note that those slides, I have revised slides that you can go grab, and it's only those 4 slides that are different. And I'll note when we get to those slides today, like which ones those are if you wanted to go grab and swap into the other lecture file. But anyways, what are some examples of water-soluble compounds that are containing the hydroxide, sulfide, carbonate, and phosphate ion? And so just to go through a couple of examples that are water-soluble, if you take potassium, anything with potassium ion is going to be soluble. So if you had KOH, that has to be water soluble. And water, what would it be? It would be potassium ion, and then we call the thing potassium hydroxide. It's going to dissociate into those ions. So it's going to dissociate into K+ ion, and then the hydroxide ion. The hydroxide ion is not going to further dissociate into anything else. So we're going to have these two ions here in solution of KOH. And so KOH is water soluble. Its ions in solution would be potassium and hydroxide ion. For an example for sulfide, might be anything that contains, an alkali or ammonium, but also calcium, strontium, barium. And so if we had barium sulfide, BAS, so the barium 2+, the sulfide 2-, that's water soluble. We could list a bunch of other examples if we wanted to. The carbonate and phosphate exceptions are only ammonium and the alkalis. So we might have, say, for the carbonate ion, maybe cesium 2 carbonate. So cesium's a plus, it's an alkali member. Not a very common example, but it is a member of the alkali cation group. So cesium, 2 of them paired with carbonate, that's water soluble. So in solution, this would be 2 cesium cations and then a carbonate ion. So we'd have carbonate ions and we'd have cesium cations in a solution of cesium carbonate and water. And then phosphate, let's look at ammonium. So ammonium is NH4+. We didn't see too many examples of this back, we named it in the naming chapter, so hopefully you recognize it. But it has a plus charge here, so 3 of them to pair up with the 3- phosphate, so NH4, phosphate, so ammonium phosphate would be soluble in water. And then even though there's a bunch of atoms here in solution, it's really just the ammonium ion, so we'd have 3 parts NH4+, and then we'd have 1 part PO4 3-, and by part I mean, if you imagine you had a big bucket of water and you put a whole mole, you put the molar, come up with the molar mass of the compound, weigh that out in grams. And so if you put a whole mole of that compound into water, you'd have 3 moles of the ammonium cation. You'd have 3 moles here, but then just 1 mole of the phosphate. So 3 ammoniums for every 1 phosphate. And so that's how we can come up with the ions in solution for the compounds that are water soluble. But if you took an exception, or if you took an example of one of these compounds that's insoluble, which is really anything else. So with hydroxide, we have ammonium, the alkali cations, calcium, strontium, barium as its soluble exceptions. Anything else you pair up is insoluble. I mentioned last time magnesium hydroxide is insoluble in water. That's one example. Another one could be if you took iron 2 hydroxide, so iron OH2, that would be insoluble. And then in solution, there would be effectively no ions, or the solubility chart would be saying if these are insoluble, then there's no ions in solution. So we don't ionize into water, so we're not getting those ion products, so we're not getting anything into the solution. So think about how you have the solvent water, you have what you're trying to dissolve into it, your compound. If it doesn't dissolve, then we don't get ions. We don't get those electrolytes into the solution. And so therefore, we would just have water above the solution and solid, generally more dense, floating at the bottom. And so no ions in solution, so these are insoluble. So not strong electrolytes, not water soluble, no ions in the solution. And then a couple examples with sulfide could be, if you took, titanium 4+ with sulfide, so titanium S2. With carbonate, if you took calcium, because calcium is not one of its exceptions, that would be water insoluble. And if you took something with phosphate, like if we took, iron 3+ with PO4 3-, FePO4 would be insoluble in water as well. So just pick any other metal cation that's not one of the soluble exceptions, and you have an insoluble compound. And so any ionic compound paired up with ammonium or an alkali cation is water soluble. We can give a few examples that involve ions that aren't on the solubility chart with these ions and know that they're soluble in water. So we don't see sulfite on our solubility chart. So if you took something like K2SO3, due to the presence of the potassium ion, you know that this must be a water soluble compound. So anything with potassium paired up with any ion, we don't see solubility trends for chlorate. So if you had ammonium, say chlorate, which is ClO3-. So NH4, ClO3, ammonium chlorate, that would be water soluble. So in solution, this would be ammonium cations and chlorate ions. And so you compare those ions up with anything and you know it's going to be a water-soluble compound, even if the anion here is not one from our solubility chart. Maybe we could keep going with this, but maybe do one more. So we could have phosphite, PO3, 3 minus. And let's imagine like that hydrogen oxyanion. So remember those things. So you could have something that looks like this, H2PO3 with a minus charge, and you compare that up with like sodium. So that would be like sodium dihydrogen phosphite from nomenclature. And that we would know is water soluble. Then we get sodium plus into solution, and then the hydrogen phosphide ion. Not a very common example, but you can sort of piece together anything you're recognizing from nomenclature from the other anions that aren't on our solubility chart. As long as they're paired up with ammonium or an alkali cation, we at least know then that those compounds would be water soluble. And the last thing I'll note here is that water solubility isn't infinite. It doesn't mean you can put an infinite amount of the compound into water. You can just put a reasonable amount of the sample into water and it'll dissolve. And each compound will have its own special solubility. It turns out solubility, like if you have a liter of water, some compounds might be soluble to 25 grams, to 50 grams, sodium chloride's up to like 600 grams. That specific solubility is a property of the substance. So just because we say something's soluble doesn't mean it's infinitely soluble. Every compound does have its maximum solubility limit. It's just the ones that we say are quote unquote soluble are reasonably high. The things that we say are insoluble have a reasonably low solubility. So low that we just say they're insoluble. Okay, so let's come back to this demo that we were looking at last time and see it again. We actually weren't seeing the correct color change, so I wanted to make sure that we did it again too, because when I mix together a solution of lead ions, which we're going to have lead nitrate serving as our source of lead ions, because everything with nitrate's water soluble. So we're going to start with lead nitrate, and then we're going to start with Ki. And so potassium iodide is going to be a source of iodide ion. And so if we have the iodide ion, say 2 of them, pair up with the lead mixed together, then they should be forming that insoluble lead iodide, because PbI2 is insoluble in water. So when this reaction takes place, I should be getting my precipitate here. This is what we call the precipitate, or the solid that forms during the course of the reaction. And then the KNO3, those ions would remain in solution because KNO3 is a water-soluble compound. So what we're really doing here is what we call a displacement reaction, or a double displacement reaction, or a metathesis reaction. We'll also call this a precipitation reaction. So this reaction has a bunch of different names, but we're just really trying to see, can we exchange these ions for each other and end up forming a solid? And it's going to be really important that for this reaction to take place, that there is solid formation. So let's start with this reaction, and then try to hopefully see that purple, the yellow color emerge. Purple over here. Next demo that we'll do. Okay, so I have solution of lead nitrate, Ki, to mix these together, and we get that yellow solid. So it's the exact same as the picture on the slide. But just wanted to make sure that we can see that what we're doing is just taking those ions of iodide and then precipitating those ions with lead. So we're forming lead iodide here as that product. And so then you can actually get solids to do this too. So if you take solid lead nitrate and solid Ki without the water, you can actually mix the solids together even without the water. And after a lot of mixing, it might take a second or two, but if we mix this up, eventually we'll start to see a yellow color emerge. So we can even get this reaction to take place without water being there at all. So you can probably see like a yellow color emerging. And so we're forming their lead iodide just within the actual crystals itself. Okay. And so what we're seeing here is just an example of a displacement or precipitation reaction where we're precipitating a compound by mixing 2 solutions together and then just seeing if the mixing leads to a solid that forms. And so so how can we predict if we get a precipitate? And so the thought process could be this. So an example could be like, imagine we're going to mix, and we have this ready to mix here today, cobalt-2 chloride, which is CO2 plus with the chloride ion, so it's CoCl2. And And we're going to mix that with sodium sulfate. Sulfate's SO4 2-, so sodium sulfate, of course, is Na2 down here as SO4, because sodium's a plus. And so if we mix these two solutions together, the question is really, do I get a precipitate that forms when I mix these ions together? Because cobalt chloride is a water-soluble compound. If you remember, chloride's generally soluble with 3 exceptions. Cobalt's not one of those 3 exceptions, so that's a water-soluble compound. When I write AQ, that's really important for me because when I say cobalt chloride aqueous, means it's dissolved in water. And in a moment, I'm going to think, well, what is my cobalt chloride solution? I guess I can think of it here, that when I have something that's water-soluble, I write AQ, and then that's telling me that cobalt chloride is really this in solution. That in solution, it's really the cobalt ion AQ and then the chloride ion AQ. And AQ just means dissolved in water. And so these little tags here are just saying AQ. And so cobalt aqueous, chloride ion aqueous, that those are in the solution. And the same thing with sodium sulfate, that those are water soluble. And so we'd have AQ here as well. So we'd have that really being 2Na plus SO4 2-. And then when I think of swapping the products or swapping the cations around and I get cobalt sulfate, the question becomes, is that water soluble or insoluble? So we have to maybe go back to the solubility chart if you don't remember. But if you check the solubility chart for sulfate, generally soluble with 4 exceptions. The exceptions, if you're looking at it, would be strontium, barium, mercury 1, and lead. Cobalt's, of course, not one of those exceptions, so this is water soluble. So we'd write AQ for that. So cobalt sulfate is really cobalt ions in solution and sulfate ions in solution. In water, it's dissolved. It's just dissolved ions. It's not a solid. And same thing with NaCl. That's, of course, aqueous. Anything with sodium's water soluble. So that's really 2Na plus 2Cl-. And so if you look at the reaction we're trying to do, it's like we're taking a set of ions in water that are all ions, and we're mixing it and losing our, what's going on here? All right, we've got our screen back here. And so we have a set of ions before the reaction, we have a set of ions after the reaction. That probably means that there's no net change. There's no actual change taking place. I don't have a solid that can form. So let's see what happens when I mix these solutions together. So I have 2 solutions of cobalt chloride. So I can do 2 different reactions. I'll do a second reaction in a minute. But this is my sodium sulfate, my cobalt chloride. And I mix them together, and there's no apparent change. So it looks like I just diluted those 2 solutions in each other. And so nothing changed here for the cobalt chloride. So I mix a solution of cobalt chloride and sodium sulfate, and I don't have an apparent reaction that takes place. There's no obvious chemical change that's going on inside of that class. So we would actually say that even though we wrote out these 2 reactions here, we can write out the COCl2 plus Na2SO4 goes to COSO4 plus NaCl, that's actually no reaction. So that there's actually no reaction that takes place here because there's no net change. If you notice, cobalt ion cancels itself out, chloride cancels itself out, sulfate cancels out, and sodium cancels out. There's no net change taking place during this reaction. So I need there to be a net change. I need to form a compound that doesn't simply dissolve into the solution in order to drive this type of reaction to take place. So the next slide kind of goes through those 2 reactions that I was writing out before, of one writing out what we call here the full molecular reaction. Now the full molecular reaction can confuse us sometimes because it looks like a reaction's taking place, but when I notice that all these things are aqueous, and then I think about what that means in terms of the ions that form, how I have all these water-soluble ions, and when I look at the ions on the left and the right side, they're exactly the same. There's no net change going on in this reaction. So it's kind of like the physical change versus chemical change. There's no chemical change going on here. So I need to change the chemical nature by forming a compound that simply doesn't become water soluble. So no net change here has occurred. We call these ions spectator ions when they don't change during the course of the reaction. All the ions present are what we call to be spectator ions. And so now let's look at a reaction where we do get a precipitate that forms. So if we take cobalt 2 chloride again, and then in this case, we mix it with sodium carbonate. So make one little change. Instead of sodium sulfate, let's use sodium carbonate. Na2CO3, also water soluble. Of course, anything with sodium is water soluble. And so I have my cobalt ions, I have my sodium and carbonate ions, but the difference is when I form cobalt carbonate, that now that compound's insoluble. Carbonate only has the exceptions of ammonium and the alkali cations, so this compound here is insoluble in water. So if I mix these two solutions together here, I should lead this compound to forming a solid, and then my sodium chloride is water soluble. So let's take a look at that reaction and get a picture of it. So just really simple now, just taking the cobalt chloride, sodium carbonate, and mixing them together. And we see first we see a color change, and then we mix here. It's cloudy. I'm not getting a lot of solid, but there is, well, actually, it's a good question where all the solid is, but there's some solid forming. Maybe it's a little slower reaction than I would have thought, but there's some like little granules in the solution. So we're getting some of that solid formation. Maybe the concentration's a little low to see a distinct clear solid form, but we're forming here that cobalt carbonate, seeing an actual color change, seeing a chemical reaction take place. And so we're forming that compound. I'm gonna look back at that in a minute and see if it has more solid in it than it does at the moment. But this is what we're forming here as a solid that allows this reaction to take place, that allows there to be a net change, a net chemical change. So is there a net reaction that occurs, and if so, what's that reaction? So we start with our full molecular reaction. Now the reason why we kind of call this the full quote-unquote molecular reaction is that we're treating the reactants and products as if they're quote-unquote molecules. You know, in that they're actually, like when you write COCl2, you might think that they're stuck together, but in solution we know that they're ionized. But we will write reactions that look like this a lot because it's convenient to write reactions this way. It's a shorter way to write the chemical reaction. But really, the cobalt chloride is cobalt ions and chloride ions. So when you see COCl2AQ, you have to think it's not cobalt and chloride stuck together anymore. It's cobalt ions and chloride ions separated due to the nature of that compound being ionic, and then it being water soluble, and it therefore being a strong electrolyte and dissociating into its ions. So sodium carbonate does the same. It's 2 sodium ions and carbonate ion, and then our cobalt carbonate forms as that solid, driving the reaction take place. Then we have our aqueous sodium and chloride ions because NaCl, water soluble ionic compound. And so then the net change here is the cobalt plus carbonate goes to COCl3. So this is our net change. This is what we call the net ionic reaction. The net ionic reaction, sometimes we write this because it allows us to see that there's a net change. If I go to write my net ionic reaction, note that I'm canceling out my spectator ions. When I cancel these out, doesn't mean that they disappear. They're still in the solution. They're just not part of the net change. So they're still there. They quote unquote watch the reaction. They don't participate in the chemical reaction directly. They need to be there because they're the counter ions. They're like how we're bringing together the carbonate. We had to bring carbonate, we had to pair it up with something positive. So to have carbonate into the solution, we had to have something like sodium present. To bring carbonate, we had to have something positive, and then also to bring the chloride, we had to have something positive to bring the cobalt in. So we have to mix solutions where there's a balance of charge, and so we need there to be the 2 plus and the minus and the plus and the 2 minus to bring those ions together. So the spectator ions still present, they don't just disappear, but we cancel them out of the net change. And so the net ionic reaction allows us to see what the actual net change during the course of the reaction was. And allows us to verify that indeed a chemical reaction occurred. And so now if I take a random solution like barium nitrate and say if you had barium nitrate, then which of these solutions when mixed with barium nitrate would yield a precipitate? So you can consult your solubility chart if you need to for this question, but think through which of those compounds, if any, would precipitate, form a solid when mixed with barium nitrate. Take a minute or two on this one if you want. Anybody have a quick thought on what the answer might be? Well, when you see the first two are nitrates, so we have calcium nitrate, lead nitrate. My thought kind of goes to all nitrates are water soluble, and also we start with a nitrate. So we have barium nitrate, all nitrates are water soluble. We have two acetates in A and B. All acetates are water soluble. So when I'm picturing this reaction here, if I take barium nitrate plus calcium acetate and I consider getting barium carbonate, I kind of already know that this has to be a water soluble compound. So the barium acetate has to be water soluble because all acetates are water soluble. And then the other product, because it's a nitrate, the calcium nitrate, must also be water soluble, just because all nitrates are water soluble. So no solid forming here. So A doesn't work, B doesn't work for the same reason. So it's kind of like I'm looking at this ion here and this ion, I'm looking at my barium and I'm trying to think, does the Ba mix with the other anion become insoluble? Or does the anion here, or does this ion here mixed with the nitrate become water soluble? Like lead nitrate's water soluble, barium acetate's water soluble, so B doesn't work. C, you almost would think work because most hydroxides are insoluble, but barium hydroxide is water soluble. So if I mix KOH, I get BaOH2, or I might consider getting barium hydroxide, but that's water soluble. And then the other product, KNO3, of course, is water soluble as well. So no solid here, two water soluble compounds, so C doesn't work. But then D works well because sulfate forms the insoluble barium sulfate. So BaSO4 now is one of the exceptions. So what I'm thinking here is for solid versus AQ, is water soluble is AQ, and it's dissolved in the solution as ions, because that's the ionization process for ionic compounds. But if it's insoluble, then it's just a solid. It just would be at the bottom of the test tube. I do see like that precipitate looks kind of peculiar in that cobalt case, doesn't it? I've never done that demo before, but it doesn't really look like the solid I would have expected. Like you see the clear solid from the lead iodide, but I think we do see a solid settling there to show that solid formation for the previous demo. But so for barium sulfate, the byproduct here would be KNO3, AQ. And so this is our solid precipitate. So D works as the precipitating agent. So we can say, like, for example, you can precipitate barium ions with K2SO4, or you can precipitate barium with sulfate ion. So we're just doing this precipitation reaction of barium. I don't want to necessarily write the net ionic. We're going to get into net ionic reactions again with acid-base reactions. But if we wanted to, we can think about how barium nitrate is barium ions and nitrate. We can think of how K2SO4 is K plus and SO4 2 minus. And then it's the Ba2 plus pairing up with the SO4 2 minus to form our barium sulfate. That's our net change. So I don't think it's too hard to come up with this reaction here without writing the full ionic in the middle. So this is our net ionic reaction that's taking place in D. And if you're not sure where I'm coming up with this, then just picture barium plus nitrate, two of them, and then picture 2K plus SO4 2 minus, and then have that form BaSO4, which doesn't dissociate. So BaSO4 doesn't dissociate because it's insoluble. It's at the bottom of the test tube. So the reason why BaSO4 on the product side isn't ionized is because it's a precipitate, because it's stuck together as a solid now. Okay, so let's get into a discussion of acids and bases and come back to this discussion. We were seeing the electrolytic behavior. In a way, I was maybe getting a little bit ahead of the material because I wanted us to see last time on Wednesday that you can have an ionic compound like, what were we looking at in the demos, like NaCl or Ki or something. We were seeing that those compounds were electrolytic. They had ions in solution, but acids can do this too. So acids can behave as electrolytes when they dissolve into water. And so some common acids are things like hydrochloric acid, nitric acid, sulfuric acid, acetic acid. You probably remember naming these from chapter 2. So we have all these acids we were learning how to name in our nomenclature unit. And it turns out 7 of those acids that we learned how to name are strong acids. And we call these the 7 inorganic strong acids. And then these we are going to just have to simply memorize, but I don't think the memorization is going to be too hard. It's HCl, HBr, HI. So it's 3 of the 4 hydrohalic acids. So if you look at the halogens, the only one not included is HF. So HF is on the weak side, Now again, this comes back to the whole discussion. When you hear me say strong acid versus weak acid, you would probably be more afraid of the strong acid, right? HF is the most hazardous, and the strong acids are hazardous too, don't get me wrong, to work with, but HF is really, really dangerous to work with. So don't think just because you know weak versus strong or dilute versus concentrated or the name implies safety. Make sure if you're working with chemicals, if you get involved in research, learn how to determine the safety hazards of working with compounds. You learn to look up material safety data sheets. If you're not doing this, if you're in a lab setting, you could be setting yourself up for a lab accident. But anyways, HCl, HBr, HI, these are strong. What this means is if I take HCl, which can exist as a gas, which you can buy this in a gas cylinder. I'd just like to point out that you can have this as a gas. And imagine you take that gas and you bubble it into water. Now, we can imagine doing this with something that's completely inert, like helium. If you take helium and bubble it through water, it just bubbles straight through the water. It's not really sticking in the water. So most substances that don't have an affinity for water are just bubbling through and not sticking. HCl turns out to have a strong affinity for water because when it hits the water, it breaks apart. And when it breaks apart, we can keep putting more and more of it into water until we concentrate that solution. So when it hits water, it's ionizing to H plus and Cl minus. And then H plus AQ, and then Cl minus AQ. At some point when I have ions, I'm going to stop writing AQ every time because if you have an ion, it has to be dissolved by water. So positive or negative charge, water has a built-in charge to it, a built-in negative side, a built-in positive side. The O attaches to or surrounds the positive charge. The H's with the positive charge of water surround the negative charge. So at some point, I'm probably going to stop writing these AQ tags because these things have to be dissolved into the water and surrounded by water. But anyways, HCl does this to 100% yield. So that's what we mean by strong, is that the acid completely dissociates in water. And what we mean by weak is HF now partially dissociates into H plus and F minus. This equilibrium arrow is what I write to imply that we don't get 100%. And so we get less than 100% yield on this reaction. It's probably more like 5 to 10%. Depends on the nature of the acid. It depends on the concentration of the acid, but we're not getting anywhere near 100% dissociation on the weak acids because that's why they're weak. We're getting some ion formation, but just not the complete formation of ions we would have gotten if it were strong. Great question. So the BCA chart with these incomplete ones, those become something you might have seen called ice tables. Or like that's one type of table, but that's like a chapter 16 topic you'll see later. So if you remember solving equilibrium problems for calculating like the pH of a weak acid, does anybody in this room remember doing that? I don't know, just because it's hard for me to gauge if you guys have seen some. If you've had AP chemistry, you probably saw that. If you didn't, you probably didn't see it yet. But don't worry about that just yet. So you can't really easily predict the amount of product you get. I could give you like a percent yield and you can solve it like a percent yield problem, but you don't see that too commonly. But anyways, the key is that these weak acids are really low on this percent dissociation scale because that's what's making them weak. And so then the strong acids, because they're completely ionizing, they completely react in water, but the reaction is to form these ions. The ions serve as electrolytes, so we call them strong electrolytes. So HCl is a strong acid and a strong electrolyte. In water, HF is a weak acid, weak electrolyte in water. And you could think because it's a weak acid to make some H plus, to make some ions, makes it then a weak electrolyte. So whether or not you're thinking of it as an acid or an electrolyte first, but those are kind of paired together. So acid versus electrolyte, because the acid process is to form ions, just not 100% of them in the case of HF and other acids. So what are the other 7 strong acids? So we said HCl, HBr, HI, so every common halogen except fluorine, but then nitric, chloric, perchloric, and sulfuric. So notice no us. So there's no sulfurous acid, no chlorous acid. So all the other strong acids, and all the 7 included, end in ic acid. It's not all the ic acids. We have like acetic acid that ends in ic acid, so it's not strong. Just being an ic acid doesn't make it strong, but the other 4 things are the other sort of key, or a couple of the other key polyatomic acids that we learned, like nitric acid, chloric, perchloric, and then sulfuric. And then sulfuric is really interesting that only the first hydrogen falls off to 100%. So for H2SO4, if we think of this step here, we get 100% dissociation into H+, and then the hydrogen sulfate ion. And then hydrogen sulfate itself is a weak acid. So I get this partial equilibrium here. So HSO4 minus to lose the second H+ to make sulfate ion, that this reaction here is less than 10%, or it's about 10%. Just to give you an idea that the first step, 100%, so strong, and then the second step is weak. Kind of peculiar, but it just means for H2SO4, you get 100% dissociation into H+ and HSO4 minus, but then HSO4 minus kind of hits a wall and doesn't completely keep going, and it eventually stops, and you're left with mostly HSO4 minus and a little bit of sulfate. In terms of how much, that becomes a chapter 16 topic later that you'll revisit in Chem 1220. Okay, so then what are some other weak acids? They're all the other acids we learn how to name. So all the other acids we learn how to name are things like nitrous acid, acetic acid. Notice that phosphoric isn't on the strong list. So if you think of, remember how we went through C, N, phosphorus, sulfur, chlorine in our naming oxyanions for carbonate, nitrate, phosphate, sulfate, chlorate, that the nitrate and the sulfate and the chlorate were strong, but not the carbonate and not the phosphoric acid. So carbonic acid is another example, H2CO3 of a weak acid, H3PO4 is a weak acid, H2SO3, sulfurous acid. We see the hydrogen sulfate ion, as we mentioned above, is a weak acid. And then all the other acids from our nomenclature. So any other acid you can picture that we learn how to name, that's not one of those 7 strong, is implied to be a weak acid and just partially dissociates into water. And so then there are a lot of things that kind of look like they might be acids, and once we see what bases are, you might think these are maybe bases, but these are neither acids or bases. And so some examples of things that maybe from their formula look like they might be acids, but they're not, are things like CH4, methane is not acidic. Methane, you can't just look at the presence of H atoms and determine something to be an acid. You have to have H atoms attached to some sort of an anion that's stable enough to exist in water. And so CH4 doesn't fit the bill. Water, you might think water might be an acid or a base. It does dissociate a tiny, tiny fraction. We talked about the autoionization of water. It's where you get the pH of 7 from, if you learned about that already. But that's like less than 10 to the minus 5% of water is dissociated. So a very, very small fraction of water dissociates so much we don't call it an acid or base. Methanol looks like acetic acid. Notice when I write CH3COOH for acetic acid, this is the acidic group, not CH3OH. Simple alcohols are not acidic, so methanol is not acidic. If it was, we probably would have changed its name to something like methanol acid or something. Notice all the acids tend to end in the word acid. Methanol doesn't end in the word acid, so it's not acidic. So there's some circular reasoning here to, trying to determine that some of these formulas aren't acidic, but ethanol is not acidic. And so I want us to kind of see that most of the acids are things that we learn how to name with the word acid afterwards. There's some of those like hydrogen oxyanions, like hydrogen carbonate, hydrogen sulfate are technically acids. That gets a little bit into the weeds of a gray area that I don't want to get too sidetracked by. Like hydrogen carbonate ion is an acid. It also acts as a base. That's like where the word amphoteric comes from. You'll revisit that later. So there's a lot of nuance here that we're just really trying to scratch the surface to come up with just a mental picture for how can we start thinking of what acids are. There are things that make H+ ions in water, and some common things that do that we can recognize here today are those common acids that we learned how to name. 7 of them do this strongly to 100%, and then a bunch of others do it in a weak fashion to less than 100%. And so then we can also classify acids by being monoprotic versus diprotic versus triprotic. How many H+ ions does the acid per mole have to give to a solution? And so the monoprotics are pretty easy because they have just one. So these only have one H+ ion to give to a solution. So we call those monoprotic. But I intentionally gave a weak acid here because you would still even call an acid like HNO2 to be a monoprotic but weak acid. HNO3 would be a monoprotic strong acid. So, but you would still call even the weak acids monoprotic if they have one H+ to donate into a solution. And so another example, HClO2 monoprotic weak, HNO3 monoprotic strong. because they have 1 H plus ion to donate to the solution per 1 mole of the compound. Then a diprotic acid has 2 H plus ions it has to donate into a solution. And so H2CO3 has 2 H plus ions to get to carbonate ion. So think of the anion you know how to name, like sulfate or carbonate. To get to there, how many ions are there for the acid to lose that are available? For H2SO4, it's 2. For H2CO3, it's 2. So these are diprotic acids, but diprotic weak and then diprotic strong. But diprotic strong only for the first, if you want to be technical. So like half of the H pluses fall off strongly from H2SO4, but not the other one. And then we have triprotic acids, and so H3PO4, H3PO3, though oddly it's actually not, but that's a little footnote, so don't get too caught up on that. But H3PO3 might be another one you look at that you would predict to be triprotic. And so you're looking here at 3 H pluses, so those are triprotic. Citric acid. Citric acid is an interesting molecule to look at the structure of because it actually has 3 of those groups that acetic acid has that are acidic. And then it also happens to have these other hydrogens here that are just kind of like the methane hydrogens. Those aren't acidic, so these are not acidic, and neither is the alcohol group. So when you start getting to like organic functional groups, it's that COOH group, that carbon double bond to O, single bond to O with a hydroxyl. When you start to get into OChem, you'll see that this group looks like this here, and that this group here is what's acidic. And you need this here next to the alcohol to make that alcohol group acidic. So having an alcohol group by itself, not acidic. So 3 H pluses, so it's these 3 here that are acidic. So these are the 3 H pluses that will fall off into solution from acetic acid, or from citric acid, I'm sorry. Now citric acid is a weak acid, it's not going to do this in water, but if I threw a hydroxide ion in, if I put something into water that can react with those H plus ions, then it can pull those H pluses off. So I can add 3 moles of OH minus for every 1 mole of citric acid, and it's going to pull those H plus ions off. That's what we're going to get into in the case of neutralization reactions. That I can take my weak acids or my strong acids, and I can add something like hydroxide ion to neutralize them to react with those H plus ions. In the case of HCl, it's going to do so because the ion's already in solution, and if the H plus is still attached to its counterpart, it's going to go rip it off and it's going to take it and form water. So before we get into that, let's just identify what we call to be bases. We talked about this briefly because we were looking at KOH and its electrolytic property last time. We were looking at ammonia and its electrolytic property last time. But the hydroxide ion is really the thing here that makes something be termed a base, because it's all about this. It's all about the H plus being an acid, and it's all about what can we add to the H plus to make water. That's hydroxide ion. So this is our acid, and then this is our base. And so the things that make hydroxide ion and water are termed to be bases, and things that make H plus ion and water are termed to be acids. And so the yin to the yang of the H plus ion is the OH minus ion. And so things that make hydroxide ion and water are termed to be bases, just like the things that made H plus ion and water were termed to be acids. And so our water-soluble ionic compounds, like if I put KOH into water, it's going to dissociate into K plus, aqueous, and then hydroxide ion, aqueous. And so I look at this compound here and I say it's water soluble. Well, the thought process kind of to me goes like this from the start. It's an ionic compound. From the solubility chart, I know it's water soluble. Because it's water soluble and an ionic compound, I know it must be a strong electrolyte. Because one of the electrolytes is hydroxide, I know it's a strong base. So that's kind of the whole thought process here is identify ionic compound. You know we can use a solubility chart, know if it is soluble, it ionizes. If one of those ion products is hydroxide ion, we call it a base. And so KOH is a strong base. Of course, we can have calcium hydroxide, barium hydroxide, strontium hydroxide, lithium hydroxide. I mean, just go through those exceptions. The exceptions for the solubility for hydroxide are strong bases in water. And then we really have just one good example of a weak electrolyte that's a base. So if you think of a weak base, weak electrolyte here, there's really going to be one good example, and that's ammonia. And there's a lot of other examples, but they turn out to be organic molecules that are a little bit tricky for you guys to recognize right now. So let's look at ammonia first. So ammonia, what goes on here, ammonia has a lone pair of electrons. If you want to think of how this works in terms of the interaction of like negative and positive charge, is you have this partial positive on the water, you have a partial negative charge on the ammonium. The electrons, if you will, this is the organic lingo. You'll learn this in OChem that the electrons attack the positive charge. It's really just the attraction of positive and negative charges brings those atoms together, and then we make the NH4 plus ion, and then we leave behind the hydroxide ion. And then what happens is hydroxide ion bumps back into the hydroxide, it takes the H plus back. And so there's this like back and forth. There's the bumps into it, takes the H plus, and it bumps back into it, takes it back. And this goes back and forth until we reach an equilibrium point. And so this is one of those reactions that's in equilibrium where we get less than 100% yield. And so say we get about 10% yield here, meaning that we don't have a strong base, we have a weak base. So we're getting some hydroxide formation, but not as much as we could have if this reaction took place to a 100% yield. So NH4 plus is partially causing water to dissociate. Adding it to water causes some dissociation. So that allows it to be termed an electrolyte, but just a weak electrolyte, because one of those electrolytes is hydroxide, we call it a weak base. So ammonia and water would be a weak electrolyte, weak base, partially dissociates. Now, the other things that you could identify would be where you have nitrogen with like 3 things attached to it, like a methyl group. But again, these become hard for you to recognize. It really takes nitrogen with a lone pair, 3 things attached to it. Hydrogen's the easiest to recognize. Sometimes we call this NR3, but again, this is like an organic nomenclature. I don't think you'll see any examples of this. So the key example of a weak base is ammonia, or things that look like ammonia, but the things that look like ammonia from your end kind of need us to understand a little bit about molecular structure that we don't really have. So it's hard for you guys in your seats right now to kind of predict if a compound would behave as a base. So we're kind of going to really just use ammonia as the prototype. So just know there are other things that are going to act as weak bases, but most of them will look like ammonia. But most of the other compounds we've talked about are not on that list. So I think that's the one thing that's useful to see, is that almost every other category of compound, like CO2, CO, those types of compounds, alcohols aren't bases. So all the other categories of compounds are not fitting into the common type of things that tend to behave as weak bases in water. So I think it's good for us to know, of all the vast different compounds we learned how to name and look at, that only this one here, ammonia, is a weak base. Okay, now this chart here is a little confusing at first. It's out of the textbook, so I want to make sure we look at it, but it's classifying the electrolytic behavior of compounds that are soluble in water. And so I want us to, like the chart here is assuming you have a water-soluble compound, assuming the compound mixes with water, what's its electrolyte behavior? And if the compound's ionic, notice that the only type of electrolyte it can be is a strong electrolyte, that there's no examples of metal-nonmetal pairs that we call to be weak electrolytes or non-electrolytes in water. Let's take, for example, magnesium hydroxide for some reason trips everybody up. I don't know what it is about magnesium hydroxide. Go to the solubility chart. Is magnesium hydroxide water soluble? According to our solubility chart, no. This chart here is assuming the compound's soluble, we look at this chart. If it's insoluble, it's like not applicable to give the electrolytic term to it. You know, like the electrolyte term is a term for something that's a solute in the solution. Magnesium hydroxide, according to our solubility chart, is not in the solution. So it doesn't get a term that goes to a solution property because it doesn't form a solution. And so the insoluble compounds are just insoluble. They're not really, we don't give the term here for electrolytic behavior to something that's insoluble. And in the case of molecular compounds that are soluble, we don't generally predict the solubility trends of molecular compounds. Like, so in terms of, you know, is HCl, HBr, HI, are those soluble in water? I mean, we're not predicting, like, presumably so, because they're acting in water and dissociating, so how can they dissociate in water if they're not soluble in water? But we're not going to show you molecular compounds and ask the question, is this water soluble or insoluble? It's going to be more, this thing's in water, is it dissociated, and if so, is it fully dissociated? And so in the case of molecular compounds, our strong acids, this is where it comes back to, remember how I kept stressing HCl, like NaCl, we can think of ions coming from it, but it's not an ionic compound. HCl, HBr, HI, HNO3, those are molecular compounds. So our strong acids are strong electrolytes. So these are those 7 strong acids that act as strong electrolytes in water. We have all of our weak acids, and then that one weak base, good example of ammonia and things like ammonia, those things are weak electrolytes in water, and they're weak acids and weak bases. So these would be things like HF, HNO2, NH3, that those are weak electrolytes. And then all other compounds are non-electrolytes. So the other compounds are things like alkanes, or like hydrocarbons, alcohols, sugars, or just the other molecules we learn how to name that aren't in the category of ionic compound or acids or ammonia. Now, you may be wondering, where are the strong bases? So if you look at this thing here, I don't see strong base here. This includes the strong bases. The strong bases, like KOH, calcium hydroxide, barium hydroxide, those are ionic compounds. So the ionic compounds, the strong bases, are already considered to be ionic compounds that, of course, are water-soluble strong electrolytes. So our strong bases just happen to be ionic, whereas our strong acids happen to be molecular. So a little bit of a difference. The things that are making hydroxide ion, things that make hydroxide ion are in the ionic category. So they're strong electrolytes because they're ICs that are water-soluble. And then the strong acids, they're in the category of the 7 of them being strong electrolytes, but on the molecular side. Okay, now let's put this together here for a reaction or two to kind of wrap today up. So let's look at the reactions of acids and bases. They will react to form a salt. A salt is just another word for ionic compounds. So they're going to form an IC when they react together, and then also water is the byproduct. And so when we do an acid-base reaction, water is really the driving force here. So when we look at mixing HCl and KOH, we have our H+, Cl-, K+ hydroxide ion. The same thought of just switching the ions around, we get water, we get KCl. Think about what goes on here in solution from an atomic perspective. We have H+ and chloride ions. We have K+ and hydroxide ion in solution. These two ions bump into each other and they form water. Water is a non-electrolyte. Water forms and it doesn't break apart. It stays intact as water liquid. To drive a reaction take place where you have ions like this, we have to form something that doesn't go back. We have to form something that's going to stay as it is and not dissociate back into those ions again. So water fits that bill. It drives the reaction take place. The KCl doesn't really do much here because we're just keeping those ions as those spectator ions. So chloride and potassium ion are the spectators. The net change here is H+ plus OH minus forms water. So my net reaction here is just H+ plus hydroxide ion. Those, of course, are aqueous, forming H2O. So H+ plus hydroxide goes to water is my simple reaction for a strong acid, strong base. Now, the only difference here with HF and KOH is that the OH minus has to go hunt out the H+ off of the fluoride ion. So it has to actually go, if you will, attack the HF. So the HF stays intact. It doesn't dissociate because it's not a strong electrolyte. KOH does. And then when we get KF's a water-soluble ionic compound, so I get K+ and F-, water liquid still, just like above. And so then only K+ here, so we only have one spectator ion in this case, it's just the potassium ion. So my net change for HF, because the weak acid is HF, aqueous plus OH minus, goes to F- plus water. And you could put AQ tags on the ions, but the hydroxide ion has to just go seek out the ion off of the H+. So it has to go attack that H+ and take it away from fluoride. And so hydroxide takes the HF away, but HF doesn't dissociate in water, so we don't dissociate it into H+ and F-. So my dissociation here for HCl, I only dissociate strong electrolytes. So I'm just thinking if it's a strong electrolyte, dissociate it. If it's not a strong electrolyte, don't dissociate it. The hydroxide is going to dissociate it by itself and do it by the reaction. Okay, we'll continue looking at this acid-base reaction into Monday. All right, have a great weekend.